So let's give a big round or warm welcome, round of applause for my man, Nikhil. I really appreciate you jumping on here and joining us. This is awesome. I'm excited to talk to you today about what it takes, what we're looking at when we want to do this work with Yugabyte and do these kind of SQL distributed databases. So I'm going to start off by going over what I usually start off with, and that is I want to just ask you how you got into tech. And I know you got some slides prepared for us later, but maybe I'll ask you a few questions. Please, anyone that is here with us today, feel free to ask questions while Nikhil is talking or while he's giving his presentation. And I can always jump in and ask him the questions. So, Nikhil, let's go ahead and get started. That was a long talk from me. So now I'd love to hear from you. What exactly got you into tech?
So firstly, thanks a lot, Dimitrios, for a warm welcome. So for me, I think tech was always the stream that I wanted to go, because I kind of grew up like a proper gamer. I probably spent 10 to 12 hours a day doing playing games on my Nintendo, things like that. So that's how I got into undergrad in computer science. And then I have a master's in computer science as well, where I kind of concentrated on distributed systems. And kind of distributed systems and databases itself, I was kind of intrigued because that was a time when people were started moving from J2EE to some cloud native microservices kind of a pattern, and they started seeing all the big data workloads come in, right? It went from being tens of gigs to terabytes of data, and that I read, being in masters, obviously we kind of probably have read through all the Hadoop, HBase, and all those papers, right? That's how I kind of developed some interest in distributed systems. And then Pivotal was one of the big data players back then when I joined them in 2015, I guess. We had Pivotal Hadoop, we had Hawk, which is a MPP-based query engine and things like that. It was a really good experience for me joining as a new fresher from college to getting into big data systems. That's how I kind of transitioned from big data, then also cloud native data services, building data APIs, data pipelines, and things like that. That's how I got into tech. So I've always been in tech. Yeah.
Awesome. So I love the transition from being a gamer and then wanting to know what's going on behind these games and figuring it out. Now, and just so we know, you're in New York now. You're originally from New York, or where did you come from, and what did that journey look like?
Correct. So I'm originally from a city called Mysore in southern part of India. So I grew up there. I did my engineering there, and I came to the US for my master's. I went to upstate New York, Syracuse University, for my master's in computer science, and then I started working in New York. So that's how I've been living in New York for close to 7 years now. So it's been great. New York, New Jersey, I've been in and around this Jersey City area. So it's kind of good.
Sweet. So today we're going to talk about a practical look at running distributed SQL on Kubernetes. And I wanted to kind of leave it to you to talk us through this and what made you want to talk to us about that.
Correct. So for me, right, I have prepared a bunch of slides that I can go through, few of them, to just get started what distributed SQL itself means, right? So I wanted to give a quick background of what distributed SQL is and why is Yugabyte is trying to build a new database called distributed SQL, right? That's something that probably interests a lot of people. So a quick background of Yugabyte itself. Yugabyte actually has its roots in Facebook. So a bunch of co-founders from Yugabyte were actually the ones responsible for the main data engineering efforts for scaling Facebook Wall and Messenger back in the day. From 2007 to 2012, I don't know if you have seen some reports, they grew from like 50 million to a billion users. So they were the ones who incubated k8s and Cassandra within
Wow.
Facebook. So one of my co-founders, Karthik, he is the one responsible for naming Cassandra. He came up with that name, right? So they had like a lot of experience building like all these high performance and like low latency, like massive scalable databases, right? One thing they saw was there was a lack of adoption of like ground up databases, like in relational workloads, like RDBMS systems, which can scale linearly, right? We didn't have that. Like all we have is like a HA mechanism for RDBMS. We have masters and a bunch of followers. We never have a sharded architecture in that case. You cannot like scale the writes the way you can scale the writes in NoSQL databases, right? So that's why they saw like there's an opportunity to bring in the like all the goodness and like the versatility that the RDBMS and relational system brings to the scalability, like to the linear scalability and the global data distribution. So this kind of Yugabyte is kind of inspired from Google Spanner paper. Like if you have seen Google Spanner is also one of the first distributed SQL databases which kind of supports globally distributed transactions, right? So Yugabyte actually followed some of those principles. It's just that we wanted to bring the entire RDBMS capabilities as well, rather than building a new query language. So that's why we started Yugabyte, where it kind of provides Postgres compatibility for a sharded dataset. So that's what distributed SQL is for us. And I wanted to talk about why the topic on Kubernetes, because there was like a lot of decisions we had to make very big, very early in when building the product. We want to build something which was cloud native from ground up, right? Like doing some of the management operations, everything is like REST API. I mean API based, and we have out of the box metrics that kind of gives out metrics to Prometheus. We support zero downtime upgrades. Software upgrades are super simple. We are able to like manage multi-cloud deployments, things like that. So those are the things that kind of interest people when we talk to our customers as well. Like what are the approach you guys took, and how are you able to simplify the database deployment for all these complex infrastructures, right, on the cloud. Like that's what I wanted to talk about in this presentation.
Awesome. Yeah, let's get into it because that does sound really interesting. And I know
Okay,
there.
sounds good. Yeah, let me start sharing my screen in that case.
Perfect. Yeah, and I know you had mentioned that you also wanted to talk about like these design considerations and the design principles, and so I
Yes,
thought that
correct.
would.
So before I go there, like I just wanted to introduce few concepts of Yugabyte itself, so that it is easier for folks to understand why we made those decisions, right? So without knowing the like the product itself, if I start to explain this, like it kind of becomes redundant, and people might not get the clear picture. Okay. Obviously, I'll just skip from a bunch of these things. I just wanted to say like Kubernetes is like super massively popular. Like everybody from big enterprises to like startups are deploying their workloads on Kubernetes. Like if you have seen any KubeCons, like all these e-commerce providers, they run their workloads on Kubernetes itself. I mean, obviously everything started with deploying stateless applications on the Kubernetes, but there has been a considerable shift in the ecosystem. Like many of the major database vendors and the stateful vendors like Apache, Kafka, Spark, Mongo, Cassandra, Elastic, and bunch of these data tool set, right? Like everybody is deploying on Kubernetes or have a deployment capability on Kubernetes, right? So how was it possible? So some of the main things like Kubernetes actually started bringing, like as Kubernetes matured, right? Like back in 2017, I guess, when we were part of Pivotal, we started working with Confluent and DataStax for bringing their solution onto PKS, which is like Pivotal Container Service, which was one of the managed services we had back then. Back then, it was so so complicated to set up a database system or any stateful system, right? We didn't have support for stateful sets. It was still in alpha. It was so flaky, and we had to use replica sets, and replica sets didn't support rolling upgrades. And volume provisioning didn't support like uh, the container interface, the container mount interface. Recently it came out, right? Like in 110, I guess it became GA. So all those things kind of matured the Kubernetes system itself to build a databases. For us, what it means is like few things that actually stands out for why it makes sense to run a distributed, database on Kubernetes. Obviously, it provides a better resource utilization, first thing, and if you don't have to wait for like months together, like to stand up a database, right? Like it used to happen before when you stand up on a vSphere VM or things like that. So now, obviously, better cluster utilization, and you'll support multi-tenancy with Kubernetes, because you can deploy different multiple clusters in different namespaces and things like that. And one important thing that Kubernetes kind of matured was with CRDs. CRDs is custom resource definitions, where you can specify your own CRD and kind of specify the logic for doing reconciling of the resources that you are utilizing on the Kubernetes cluster itself, right? So every day two operation for a database is different. And the way to implement that is obviously through CRDs. So as CRDs matured, more and more database vendors started deploying operators. They can do a lot of automation of their day two operations. None of those things needs to be manual, right? So that's why I feel like a lot of database vendors started to get deploying their data services on k8s. When I gave a brief background on Yugabyte, obviously it's has its roots in Facebook, and a bunch of co-founders, like everyone, are from Facebook.
And do you mind if I stop you real fast on
Yeah,
along the lines of that maturity and how you've seen it change from 2017 till now? Are
yeah,
there things that you're actively looking ahead in the future to, and you're expecting to
correct.
change in the next 3 years, or even just within the next 24 months?
Yeah, I mean, I don't know if you have not seen, like, one of the things that a lot of people, a lot of developers, or a lot of companies working on is like the two things. One is bringing a native API gateway support for Kubernetes, like, and also service mesh support for Kubernetes, right? There's like Istio, there's VMware has its own, and Google has its own, things like that. So that's where more maturity will come in on Kubernetes, like how to manage the traffic within the Kubernetes cluster itself. And one other thing as a database company that I am looking forward to is like support of like some of these newer age database vendors, newer age block device vendors, right? Block storage vendors who provides native capability for like data storage management. So which means like right now, if I have to build my database, I need to know what is the storage classes for different storage providers, right? Like GCP, it is different. EKS, it's different. If I go to vSphere, it's different. OpenStack is different. So I don't have to maintain that thing where I have to test the compatibility for each and everything. So there is like these vendors like Portworx who kind of abstract away that layer, where they take care of all the complexity of managing the block storage. And for me as a database vendor, all I care is like I'll make a PVC claim and I just need to get the PV right. So that's another thing where we see some lot more adoption will come in. I think in the Kubernetes for stateful workloads itself, as and when more and more customers start to productionize their data workloads on Kubernetes, I see those things to be super useful.
Yeah,
I
for
mean,
sure.
Istio at least is going to be super useful because it's going to solve a lot of things. Like it's going to solve you like encryption between your clients and like databases. It's going to support some authorization for your traffic and things like that. So I think Istio or any service mesh is going to be like next 24 months. Probably that's going to be like the most interesting thing.
Perfect. All right, I'll let you get back to what you were talking about.
Yeah, cool. We talked about the brief history. Like, okay, I what distributed SQL actually means for us, right? So distributed SQL for us means any of the other database vendors that if you talk to who are part of distributed SQL, one thing they talk about is like they are massively scalable, which means they can horizontally scale. So most of the databases can only scale vertically. You cannot shard the data, right? Generally, like with the distributed SQL databases, the first notion you have is you can partition the data, you can shard the data on commodity hardware. And also the next thing that they bring in out of the box is the geo distribution of data, which means as and when more and more architecture embrace global apps, right, where they deploy the applications across regions or across cloud and things like that, you need to have the data also reside in the same place. So for better experience, HA and things like that. So geo distribution is provided natively. And SQL capabilities, where you can provide all the RDBMS features for to some of these new age stuff like scaling and geo distribution. If you're able to bring all those capabilities to the developer, on top of that, where you can build resilience like HA and fault tolerance for cloud outages and things like that, that's going to be a very useful product to be have in your system. Like even if you have cloud outages or region outages, you still have some data somewhere where you can keep your business operation going, right? You if per se, if US East of AWS goes down, it shouldn't bring down your entire business, right? That shouldn't happen. So distributed SQL kind of tries to solve that. For us, we kind of fit into all these three characteristics for distributed SQL. Obviously, it needs to be highly performant. You need to have low latency, and we need to be cloud native, which means you should be able to deploy on any of the clouds providers, cloud infrastructure, whether it's private cloud, public cloud, on platforms like Kubernetes, Cloud Foundry, and also it needs to have an open source adoption in the community. Like if you don't build any community around your product, it will be like another big oracle, I guess. I mean, open source community, right? You'll just start building in vendor lock-ins and things like that. So for us, that's why we kind of open source a product back in 2018. Like at core, everything is 100% Apache open source. Like if you guys are interested in looking into contributing to the project, you can come and check out our issues page and or join our Slack. We are very responsive there, and you can get some swags as well from Yugabyte team. Obviously, we are not the only players in distributed SQL. Like, why one more database, right? Why one more database called Yugabyte? There's like few things that we kind of compare Yugabyte against. That is firstly Amazon Aurora and Google Spanner. Those are like some of the more established players already in the market. So Amazon Aurora, if you have not seen the reports, they are like one of the fastest growing AWS services out there. The reason being they kind of provides a highly available RDBMS system, which can provide you HA, but not scaling. You cannot write scale still. There is like some limitations to it, but you can provide a HA. But what Google Spanner did is Google Spanner took a different route. They wanted to build a completely new database, which is horizontally scalable and strongly consistent based on graph consensus algorithm and atomic clocks for doing distributed transactions. So this is one of the first truly globally consistent databases that came into the market, which kind of backs Google Ad Engine and things like that. But one thing about Google Spanner is it is not fully RDBMS system. There's like a bunch of features like foreign key constraints and all those things are missing in Google Spanner. So they kind of went ahead and built their own SQL syntax, which kind of has its own limitations where you have to refactor all your existing apps and all the tools that you use with your database needs to be rethought out, things like that. So that's why Amazon Aurora probably has more kind of utilization or adoption in the market than Google Spanner, but both are really popular projects. So what Yugabyte wanted to do was Yugabyte wanted to take all these goodness or like the versatility of an RDBMS system and bring it to the Google Spanner like horizontal scalability and globally consistent transaction. That's how Yugabyte was. That's like the motto or like the mission of Yugabyte to bring in the distributed SQL features to the global scalability. The way we do that is we have a layered approach for doing it. obviously, like even our obviously it's a clustered database, and even our internal the way the transaction and all works is inspired from Google Spanner. It's based on Raft consensus algorithm. We don't use atomic clocks, we use logical clocks. There's like a really good presentation one of my co-founders did on explaining how we use the logical clocks and how the skews and all those things work in ours, explaining how the distributed transaction works when we deploy it across multiple clouds, right? So that's a really good talk that if you guys are really interested in how our internals work, it's a really good talk to, you can just Google for Yugabyte logical clock
Yeah, we can
algorithm.
link to that too in the show notes.
Yeah, I can do that. So yeah, where was I? Like probably we have two layers, right? We said we follow layered approach. So at the bottom we have something called as DocsDB. It's a derivative of RocksDB, which is highly optimized for our distributed transactions the way we want it to be done. It is actually the one which is responsible for doing the sharding of the data, providing strong consistencies, provide ACID transactions. On top of that, we have a pluggable query engine where we support two APIs. First, we support like a fully relational SQL API, which is Postgres compliant, which is for relational workloads. And also we support a second API called SQL Cloud Query Language, which is a NoSQL based data access, which is Cassandra compliant. Cassandra require compliant. Depending upon the use case you have and the access pattern you have, you can architect your applications for either of these APIs, right? Like if your workload is always going to be a key fetch, and if it's going to grow to terabytes or hundreds of terabytes, obviously having a NoSQL Cassandra-like query access makes sense. But if you have a lot of queries, a lot of joins and indexes that you use while querying the data, YSQL API is the one that you need to architect against. So any questions? This is like the crux of what Yugabyte provides out of the box. So any questions on this?
So I've got a question while we're waiting for people to type in the chat if they have anything. This might be a good opportunity to jump into what I had asked you before, but I didn't want you to get too far into it before we were actually in the meetup, on how the latency between nodes impacts the commit time of a transaction.
Yes, let me get to that part. Before that, in this slide, I just wanted to say Yugabyte is it's like a shared nothing architecture. Like every node is identical and has the same thing, like apps can connect to any of them and fetch the data. It need not go to one particular node to fetch the data, right? So going one step further, this is where the question Dimitrios asked, we can explain that, how it actually works. So within Yugabyte, each table is actually split into what we call as tablets. Tablet is nothing but a shard, right? So if I have a 4-node cluster, my table, say if it starts out with 4 tablets, right? It kind of spreads across all these nodes. And each of those tablets is a part of a Raft group. Raft is the transaction consensus algorithm we use for internally to maintain highly consistent system, right? So the way it actually works is each tablet, whenever the data gets written into a tablet, it makes a Raft call for making the copy across all the other tablets in the cluster, which means if I have a replication factor of 3, which means like I have 3 copies of data, one primary and other 2 which acts as a backup. So Raft consensus algorithm will make will go ahead and copy the data, or will go ahead and commit the data on these 3 transactions. Internally, there is a logical clock that we kind of maintain for these transactions. It need not be atomic clock, right? Like we are not considering that everyone has an atomic clock lying around. We still are based on a logical clock, and we kind of maintain the skew, or how much the clock is skewed between the nodes to figure out which transactions wins the commit, right? So obviously in such cases, it does matter how the latency of the latency between the nodes. So we have for us, like if I use NTP, right? NTP has a probably 5 or 6 milliseconds, I guess. That's what it returns the clock time. So, and between that, we have 30-second timers or waits when we try to do the retries of the transactions. So obviously, if I'm doing a transaction across multi-cloud or multi-region, if the transaction takes more than whatever the threshold I have, the transaction will fail. For a highly performant transaction, we expect all the writes to be going to a logical group of nodes which sit in the same data center, so that you'll have fast writes. And then internally, it can take care of writing it to the other cluster, maybe in the different region, or other nodes which are in the different region, which is kind of the H for the HA scenario,
sure.
right?
Thank you for that.
I mean, it was a pretty detailed explanation. Like for simply putting it together, the latency between nodes actually do matter when you are doing a highly performant system. We have built some guardrails around how much clock skews that you can handle within a cluster and how many retries you can do for a transaction. So all these things only come to the picture when you are doing a transaction. If you're not doing a transaction, these things will not come into the picture. Hopefully that answers the question to a certain extent. Okay, cool. Yeah. And also one other thing, that if you see, like we have two components in the cluster. One is called YB master and the T server. YB master is nothing but like a coordinator set of nodes which are responsible for election of leader election of the tablets. So in the raft consensus algorithm, always you'll have a leader and two followers. So this master is responsible for coordinating that leader election. So there is no traffic that was gonna go through that master. It is just for coordination purposes, and all the data access and the data storage actually happens in T servers, which are the ones which is responsible for storing the node, storing the data itself, which is based on DocDB. So yeah, that's how we are able to scale PostgreSQL. We are reusing the upper half of Postgres query layer in our deployments, and underneath what we have is the DocDB layer where we do a lot of push downs, which means that we are not bringing all the data to one of the nodes where the query was received. We kind of take that query, and we have our query optimization algorithm which gonna do push downs of all the queries to other DocDB layers, so that wherever the data actually resides, it performs its operation there. The queries are filtering, whatever, right? It goes through the DocDB layer, and only the results are returned to the SQL. So that's how we are able to scale the relational workloads with YugabyteDB. Yeah. Actually, it's like this itself is a whole topic. I will not, we can do one more session for that if there is an appetite. But I just wanted to go directly into like some of the Kubernetes topics, right? So these are the three main deployment topologies we kind of see that our customers use. So obviously, one is within a single region, you can deploy across multiple AZs. So if it's a AWS East region, you can deploy it on 1A, 1B, 1C. This actually provides you failover between, like whenever you have like a zone outage and things like that, your database will not go down. Still, you'll have a highly performant system running. The other thing is like single cloud multi-region. Say you can have the database deployed across US East, West, and Central, and you can mark one of the regions as a leader region, so that all the writes go to that region, and the reads can go to any region, and it can be consistently read, because we are still saying we are a highly consistent system across regions as well. And the third approach is you can deploy Yugabyte across multiple clouds as well. The same cluster, the nodes will be spread out or spread across multiple nodes. So a lot of our customers have this setup where they have two zones within their data center, and the third zone will sit in a public cloud, so that they can easily scale out the cluster, or they can have, in case of data center outage, they still have availability. So these are the main topologies that we support with Yugabyte. And currently on Kubernetes, the first one, which is the multi-zone support, that's the one that is currently we support. And we are working towards supporting multi-region on Kubernetes. For that to happen, Kubernetes itself needs to provide multi-region support, right? It should allow how to do a DNS lookup of the pod in a different Kubernetes cluster, things like that. That is only available in GKE. We do support it on GKE for on-premise or other installations. We are thinking of working with Submariner or some of the other things that are new to the place to kind of support this multi-region deployments. So in today's talk, I'm gonna just go over like what are the design decisions that we had to take for single region deployment of Kubernetes. Okay, now coming to the actual stuff, YB on K8s. So as I said, we wanted to develop a cloud native database from ground up, right? What does that mean, right? Like there's like, obviously we had to do a bunch of design decisions early on to figure out and kind of define what those actually means for us. So first thing, obviously, our relational workloads, we need to be able to scale them on demand. We are able to do that by sharding our data across all the available nodes. And the second thing that we wanted to support was everything should be API driven. Like if you want to determine the state of the cluster, if you want to do some admin operations on the cluster, all those things should be API driven so that it can be easily integrated with any of your CI/CD pipelines. And similar to how you might have done your stateless application, like part of your like say how you deploy stateless application using Jenkins or any of your CI/CD provider, you can do the same thing with Yugabyte, I mean the database also, and also know the state of the cluster. And the second thing is we should be supporting out of the box metrics and support some of the newer metrics providers like Prometheus. We kind of pack Prometheus in all our nodes, so which kind of gives you metrics. You can hook up Grafana or whatever dashboard you want to Yugabyte. You'll natively see all the metrics coming up. So these are the things that we had to like think through when building the product, and this kind of provided us like step up when we were architecting our solution for Kubernetes. Like in Kubernetes, when I'm building CRDs, right? So let's just take a situation where I want to like upgrade my cluster. So during my upgrades, like I need to first understand what's the state of my cluster is, right, in the CRD itself. Like in the Go client, either I need to write bunch of bash scripts to find out what the state of the cluster is, or I can make an API call to determine what the state of the cluster is, right? So using that, I can reconcile the operations. So if the cluster state itself is unhealthy and I kind of go and start doing a rolling upgrade of the cluster, obviously it will fail and you'll burn yourself. So all these things you can actually implement all the edge cases using CRDs and operator. And it was easy for us to implement all those things because we had all those things already available readily for us using APIs. We didn't have to build anything new just to make it work on Kubernetes. And since resiliency plays a very important role when you're deploying to cloud, you never know when there is a failure of your pod or the nodes that hosted by Kubernetes or the entire region hosted by Kubernetes, right? So in that situation, you need to know how your product works in case of infrastructure failures, like how much failure you can take and how can you automatically recover the data, backup the data, and things like that. We support all those things out of the box. Like you can specify automated backups, and you can restore another cluster using those backup and things like that. And the second thing, which is I think most of us would already know about, is like supporting zero-time upgrades is super important. You cannot take any downtimes when you are in production. Like having a downtime for even an hour, 2 hours, like in the new age cloud native applications, right? That will that will be a very bad experience for the users. No one, yeah, that won't fly, right? Like that's why you kind of have to support zero downtime upgrades. The way we kind of do it, we kind of do zero downtime upgrades, like doing one pod at a time or batch of pod at a time, depending upon how comfortable you are based on the load you get, things like that. So you can specify all those things in our when you set up the cluster itself. So Yugabyte is deployed as a stateful set on Kubernetes. So we have two stateful sets, as I said. So we have one for the YB master itself and one for the YB T server. So those run as a separate pod within a same namespace. So these six, like a minimum minimum cluster of minimum Yugabyte cluster on Kubernetes will have 6 pods, 3 masters and 3 C servers. Masters will be of master consumes lesser resources like 2 vCPUs or 4 gig or whatever. T servers are the one you need to size it based on the workload. If you have a workload where you want to store 100 gigs of data, 100 or 100 terabytes or 10 terabytes, whatever, right? So you can have to size your disk, you have to size your CPUs and RAM accordingly. And we kind of provide a t-shirt sizes like small, medium, large, depending upon how much data that you want to store. I'm going to walk you through all these things in our in the next demo and getting to that. On top of that, obviously, it's a stateful set. We have headless services that kind of takes care. If you are running an application within Kubernetes cluster itself, you can just connect to one of the clients to headless service of the T servers. It can get the data access. If you have an app which is running outside of Kubernetes cluster, we can expose a load balancer where the traffic can go through the load balancer. Let me quickly give you like a live demo of what I explained right now on Kubernetes. So this thing, what you are seeing right now, we call it as Yugabyte platform. So this is the one, it's like an orchestrator. If we are using some other vendors out there, like probably MongoDB, I guess MongoDB has a similar product called Ops Manager, where they take care of orchestrating their database using that. So Yugabyte platform is our orchestrator for Kubernetes and other cloud providers. So first thing, the Yugabyte platform itself, it runs as a pod within Kubernetes. So it's nothing but Node.js in the Play framework app that we have written which can do all the day 2 operations and creation. It kind of supports the DB as a service for us on any cloud provider. The first thing that anyone can do with Yugabyte is we kind of support all the cloud providers out there in the market today. So we can take care of orchestrating our like creation of our clusters depending upon the cloud provider that you want to do. So in my case, I am doing a managed service, managed Kubernetes service on GKE. So that's why I have configured I have a configuration which supports the Kubernetes deployment. So if you take a look on what the configuration actually itself does for us is just takes kubeconfig and a bunch of service like service accounts where do I get the image, and also we are specifying the regions, like where do I have to deploy my cluster and things like that. All these things you define here. One important thing we also do as part of this, which I'll come back to as I go through my slides, is the storage classes, right? It's a database, and if you see number of CSI drivers out there for Kubernetes, it's like there's a long list. All the like traditional providers like Dell, EMC, Dell EMC, VMware, everyone has their own way, and GKE, AWS, everyone has their own stuff, right? So we didn't want to bake our product against a particular vendor. So we kind of support any storage class which has a very good SSD performance. So the 99 percentile should be good enough that so that you can have a highly performant system. So that's all we have as a prerequisite. So for that reason, what we did was we provided an option to specify the storage class that any operator want to run against. So we don't have any hardcore requirements around the like hardcore tie-ins. Like we have requirements of how SSDs need to perform, but not what kind of SSDs or what provider we need, things like that. There is no vendor lock-in to your disk providers as well. And if you want to use like all these new vendors like Portworx, you can just go ahead and we work against those products as well.
Yeah, and can we jump into that a little bit more, like this idea of the new vendors or this container attached storage and how that would work? Like, because I know there's Portworx, there's open source ones like
Correct.
OpenEBS, and
Yeah.
what does that look like if it's integrated into this?
So like if you know how some of the CSI providers work, they kind of create their own drivers, right? So they create their own drivers and they register or deploy their drivers in the Kubernetes cluster. For a database vendor like me, it doesn't matter how they orchestrate the workload behind the scene. For me, the only contract for me is whenever I do a PVC call, I should get a PV back, which can be attached to my uh, container. How that gets orchestrated behind the scene, it's very transparent to the application here. So each of them have a different way of doing it. It's based on the storage. That's how they create a storage class and the corresponding driver. So if you see a storage class definition of these drivers, right? So this is like the CSI vSphere VMware.com. Like that is one of their storage class provider or the storage class driver. Similar to that, currently what I am using is I'm using the Google Cloud Storage, right? Like I'm using the GCS for my demos here. So that's how it becomes transparent for the application. So it depends on how like the what storage class that you have. I quickly define the storage class I have.
Oh, nice.
So if you see, I have the GKE PD storage class for me, right? Like I have two things. Like I wanted to have like a fast SSD as well and a standard one for demo purposes. Like if you're doing a performance test or things like that, I'll just use SSD. If not, I'll just use a lesser costing disk drive, I guess. So similar to this, you can specify any number of storage classes you want or whichever provider you have. And all I need in Yugabyte is for you to give me which storage class to use. And that storage class needs to be installed on the cluster already. So some of the earlier versions didn't have this capability where they always used to say, okay, this is the GFS, cluster FS is the only supported version I have, or things like that. So we didn't want to do that kind of hard requirements when it comes to disk itself, because
Yeah, it makes it much
Kubernetes
more
has a wide
a
variety of
seamless integration,
correct
it seems like.
seamless integration, right? Yeah. And also even in that, there's like few things that we can do to perform uh, ensuring the high performance, right? So we do support local storage base. Like if you have a local storage where you want to pre-provision your SSDs. So some of these big enterprises, they don't want to just spin up any number of SSDs. It's an operational nightmare. So what they do is they pre-provision it and they give you like, this is the disk that you want to use or things like that. So that's what we kind of recommend when if you are running very high performance systems on Kubernetes. Like if you're looking to run like hundreds of Ks ops per second, things like that, your SSD performance matters a lot. So all these now GKE kind of provides good stuff, good throughput for IOPS for SSDs. But we have seen very good performance on EKS for C54X large VMs and the EBS that gets attached to those VMs. Like most of our pers that we kind of do that, and it is linear, like directly dependent upon how good your SSDs are the performance of the cluster is dependent on that. Like
Hmm.
for any database, that's the same way, right? So these are some of the like trade-offs we have on the storage side. So pre-provisioning, obviously, it kind of it's more manual than dynamic provisioning. Dynamic provisioning provides you more easier way of spinning up the cluster. But when you go to production, having some control of what kind of SSDs you use, we kind of like recommend using a local storage.
And quick question here from the chat.
Yeah.
They're wondering if this requires block storage or does file or object storage work as well?
It requires file storage.
Okay,
So
perfect.
we use like any NVMe attached storage that like EBS is fine, and or Google PD disk or persistent disk, right? That's what they call it. So that's what we use.
Excellent.
Okay, when it comes to database itself, there's kind of three categories. Like first thing for us, at least in the distributed SQL database, we wanted to take care of the disk performance. Disk performance is super important for us. So that's why there are like different decisions that we made, where we provided the capability for choosing the storage of their choice, and also we provided different ways of mounting the storage, like or using the storage. And the second one being that for the data resiliency, because we don't want all the pods to be deployed in the same node, right? In a 3-node cluster, like if I have a 3-pod T server or 3-pod cluster, if all the pods goes on to a single VM, so then there is no point in resiliency there, right? Like if I lose that node, obviously, like I'm losing the entire cluster. So for that, obviously we have built a bunch of anti-affinity rules so that the pods gets distributed correctly. And also whenever we are deploying like a like in a particular region, multi-zone deployments, we kind of read the labels that are given to a node to determine where that pod has to go. Things like that. All those things are taken care when we are deploying the cluster using our operator. So these are like pretty seamless for a developer. So as a developer, all I need to do is like specify the bunch different regions that I want or different zones that I want to deploy my cluster in. So and then Yugabyte internally takes care of deploying the pods on these nodes or across these zones. So those things we do it based on the anti-affinity rules that we build in our stateful set deployments.
So I don't want to totally throw you off, but I have a few more questions. I know we're getting low
Yeah,
on
go ahead.
time. So if you want to pound through it, go for it. But otherwise, I'll ask a few questions.
Oh yeah. Like this is all I had. Like few other things that I want to talk about is the day 2 operations, like a database perspective, how we handle. Like you can go ahead and ask questions for me.
Yeah, mainly one thing I was wondering if you could talk to us about is just different use cases you've seen. I know you touched on it a little bit in the beginning, and when is this going to be something that I want to use, and when is it something that potentially it's not for my needs right now, right?
Correct. So for now, what we are saying, our CQL, like as I said, we have 2 APIs, right? One is a CQL API and a SQL API. So CQL API is a straight NoSQL replacement if you require transactionality in your data access. So there are like workloads. There's like a lot of workloads out there who use NoSQL, but they are struggling with a non-transactional way of NoSQL works, right? But if you have a use case where transactionality or the consistency of the data access is super important, you can go start using SQL, Yugabyte SQL. For SQL, this is a little bit. There's like few other caveats to using SQL. So right now, as I said, it is a PostgreSQL compliant, right? So if you go to Postgres, there's like a lot of there are like a considerable amount of ecosystems that are there in Postgres, like different packages. There's like a lot of packages that we have, Postgres has. So we don't have the complete let's just say parity with PostgreSQL yet. So we are targeting all the new age cloud native applications that are planning to re-architect their existing relational database so that it can have like a domain specific data access, right? If you are doing that kind of relational workload, we are expecting SQL to go there. If you have a database system where you perform like a lot of joins and have a lot of procedures and things like that, uh, we don't uh, we don't feel comfortable yet for those kind of use cases. That's
Awesome.
where we are actively working on, because that's where we want to get to. We want to like be in the same realm of oracles and postgres of the world. So we are not there yet.
And I see another question in the chat asking about when you would recommend customers run Yugabyte on Kubernetes versus other deployment options.
Uh, that's a really good question. So that actually has two answers to it. Like the product itself uh, works fine on Kubernetes cluster, but we need to have the maturity that built into the ops team of the customer or the development team who is productionizing this on Kubernetes itself, right? So you can burn yourself very quickly if you don't know what you're doing on Kubernetes. So those things are super important. Like you can very quickly go ahead and deploy the cluster, but what about the day two management, right? Like how easy for you to deploy, maintain your backup, restore, and things like that. So if you have maturity of maintaining a Kubernetes cluster itself, or the Kubernetes environment itself, then I feel I strongly advise or strongly recommend deploying it on Kubernetes. Given that you have all the high availability on your like even in your network layer and the disk layer, if you have all those things built into your Kubernetes cluster, then I think you can easily deploy a operational database on Kubernetes.
And
So
I
yeah,
think you
good.
said it perfectly there, and that's kind of why we're here, right? Like you can burn yourself really easily on Kubernetes, and that's what we're doing here. We're trying to learn and share this information so we don't get burnt, or we at least see how others got burnt, and then we can learn from their mistakes.
Totally, obviously, right? Like I've been doing this from 2017, like trying to run databases on Kubernetes. It's not like been a happy path always. There's been some roadblocks. There's been a lot of back and forth with customers.
So
It's kind of an ongoing conversation.
yeah, and along those lines, that same question I like to ask people when they're on here is, can you tell us a war story? Do you have any stories of when you or somebody that you know or a customer that won't get named got burnt?
I mean, I uh, let me just say this, right? I cannot give out names and things like that. Obviously, the point one or the V1 versions has been challenging. Like back then, like when we were working with Confluence of the world, like first thing, obviously, we started moving all the messaging brokers, right? Like everybody wants to move their message brokers there. Uh, so we have had situations where due to the flakiness of the underlying infrastructure itself, we have had issues. Like if you have a disk which is not able to reattach to a pod, obviously you have an outage. So we ran into some situations like that pre CSI. So uh, however, the impact wasn't that great because not a lot of people are running their entire workload on Kubernetes yet. That at least the customers that I've worked with. So they will have like 20% of the traffic going to a Kubernetes cluster, the rest going somewhere else, right? Whatever the other deployments they have. So now, as we see more customers using, like I saw recently, like HBOs of the world, they ran their entire like during the Game of Thrones times, right? Like the entire traffic was getting served through their Kubernetes deployment. So that was pretty awesome. Like they kind of talked about that in KubeCon in 2019. So but still they were only deploying stateless workloads. Like stateful workloads is like starting now to next 2-3 years. How people adopt stateful workloads is the ones. So we have customers who are running stateful workloads on Kubernetes, but those are all like startups. So startups are they're easily persuaded to run on Kubernetes than enterprises. When you go to enterprises, and also it's a database, you need to have a lot of other things around that, because you need to have compliance built in, you need to have security built in. All those things comes into picture, and that's where we are trying to have more adoption. That's the reason we want to do such meetups, so we can have more customers try out and put it into production.
Beautiful. Well, if anyone wants to continue the conversation with you, I saw you just jumped into our Slack channel. And if anyone wants to try out YugabyteDB, there are the links right there. We'll also put them into the show description if you're listening to this.
And also, like, if you're anybody interested in sorry to cut you off, Dimitri. Like, I just wanted to do this. I was told by my marketing people to give a shout out for this thing. So if anybody is looking to interested in doing distributed SQL or hardcore software engineering problems, so we are hiring actively. We are a Series B company. Like, if you are anywhere based out of in the US or Europe, I think when you are doing in Europe these days, so you can reach out to us on Yugabyte Careers. There's like some open positions out there, and if you want to contribute, you can join our community as well.
Excellent. That is great to hear. Always love that. Hear you're hiring in times like these. So if anybody out there is looking to join the team, reach out. And Nikhil, I just got to say thank you so much for joining us today, for explaining what you're doing with Yugabyte. I could have talked to you for a little bit longer, but I guess I shouldn't have had that 2 minutes of music playing in the beginning, so we could have taken advantage of all of the time. Next time we chat, I will do that for sure. And so everyone that is joining us and here with us, thank you all for listening in. We are here next week, same place, same time. We're going to be talking with Ren Lee, a barista. So, Nikhil, thanks again. Everybody out there, really appreciate you listening, and we will see you next week. Take care, everyone.
Thanks. Bye. It was awesome.